Log on, tune in, find out. Another good idea from Cambridge.
From Cornell University.
Okay. Thank you, Lee, for that unusual introduction. So, as with everybody else, I am delighted to be here. This is a great place. And given that it's Cambridge, I had to get the word philosophies in here somewhere. But this talk is definitely not that highfalutin. In fact, I hope one of my central themes here is that I'm talking about something that I don't think exists. And so I'll try to make that a little clearer as we get further along. Right, so a bit of an outline. I'm going to go through a couple of examples, and I think those two examples will bring out some aspects of this particular problem. And then I'm briefly going to talk about something called the optimization community. The optimization community, to me, means mathematical programmers. So these are the folks that do linear programming, non-linear programming, that sort of thing. And I want to sort of bring in something about what they do, just to make a very small point. And then I'll try to sort of wrap up. So first of all, let's try to agree on a few terms, because we do have a few different folks here. So in my head, a simulation model is a discrete event or Monte Carlo simulation, not a finite element method or something like that. So definitely talking about stochastic simulation, and that's sort of essential to what I want to talk about here. And input distributions and parameters are the things you sort of stuff in there. So what's the inter-arrival time between customers? What's that distribution? What's the rate? What's the service time distribution? How long does it take to serve customers? Those are all distributions, and we don't know what they are. We don't know what they should be. And according to Lee, they're changing by the second. So we've got to be a bit careful there. But then there are different flavors of uncertainty about what those things could be. So model uncertainty here, I'm going to take a fairly humble approach to this. I'm not going to say that I don't know anything about this model. We know something about the model, but we don't know what distributions to plug in. Is it normal? Is it exponential? Is it gamma? No. Oh, it's beta, right? Wasn't that what you said? Yeah, it's beta. Okay. So model uncertainty says, which parametric family should I use? And then, sorry, Russell, I know you're a non-parametric bloke. And then parameter uncertainty says which parameters, what's the actual number that I plug in for the arrival rate, that sort of thing. So input uncertainty is both issues, and you'll see I'm going to completely brush aside the details. I'm going to ignore them in good fashion here to sort of avoid getting hard questions on that stuff. So one question before we move on, though, how do we think of this simulation model? What is this thing? If we think about a simulation model as a function evaluator, right? So a simulation model is, say, an Excel spreadsheet or something like that. You plug in some numbers, you get some numbers out. And it just happens that you get sort of different numbers out each time, but if you average them over a lot of runs, you'll get the same answer. If you think about it from that perspective, it's really just a function evaluator, and then there is no such thing as input uncertainty. You plug in some numbers and you get some output. What you do with that output is your business. Then that's a completely coherent philosophy as far as I'm concerned. That's fine. Okay, go and do that. And that's something that I think Bruce Schmeiser taught me, and I've sort of taken that to heart. I think that's true. If you view the simulation just as a box for evaluating numbers, there's no such thing as input uncertainty. But what if you think of it as a tool for helping to make decisions? Or even, we don't really believe that our computer models completely make the decisions themselves, but what if we think along those lines? So now what I'd like to do is go into my first example. So the presidential election in the US in 2000, here is Florida, and it was originally called for the Democrats. And then, interestingly, that same night, it was called for the Republicans. And of course, then there was this, we were all sitting around the TV thinking, well who's won the election here? Because it's all swinging on this place. And it just went on and on. And so no one knew for actually it was a couple of weeks, wasn't it? Yeah, okay, great. So no one knows who's won the election. Good old US, they've got the perfect electoral system according to them. So then you get this kind of thing. This guy's trying to figure out who won what. Now, you can see all the little things that are sort of punched out here, and that's because the Americans, they don't want things to be too simple, so of course you have to vote on everything when you're voting for the presidential election as well. You even elect, I think there's someone that's sort of the chief of drains for each county. I kid you not, this is something they vote on. They're insane. So then you get all this question, is it a dimpled Chad, hanging Chad? These are all Chads here apparently. Who were these people intending to vote for? So there was a big stink. The question was, who did people really intend to vote for? And so there was a big push, after it was finally declared Republican, there was a big push to, through this act, to ensure that people could vote and then ensure that what was recorded was what they intended. And so that led to the push for these voting machines. So this is what they want. You've got to replace this punch card junk with what we really intended. And that has led to different kinds of voting machines. This is one style of voting machine. This is a voting machine where you go in and you do everything on a touch screen. And unfortunately, it's not, the elections are not just go in, who do you want for president? It's who's the drains guy, who's the sheriff, who's all these other folks as well. So it takes a while to vote. So now, those things you can see are a little bit more expensive than a pencil, right? So you've got to be a bit careful how you allocate those. So here we're looking at Franklin County in Ohio, and each little sort of division in here you can see is a precinct. And voting machines will be allocated to those precincts, and people vote inside their own precinct. And so there's this question, how many machines should you allocate to each precinct? And it's a big deal, because in the 2000, I think this was one of the interim ones, I think in 2004, I'm sorry, queued for as much as 10 hours. So people really took this seriously. They screwed up, right? They didn't do this very well here. There's a lot more to this story. There's a whole litany of sort of sad issues around this, but this is the main issue that we're going to think about, is how many machines do I allocate to each precinct? So I went to a talk in 2008 at a conference, October 12th, 2008, by a fellow called Ted Allen, who was actually doing some calculations for the Board of Elections in this county. And he had a simulation model to predict precinct-specific waiting times. And along comes QTG, queuing theory guy, right? So, dun dun dun, in I go. I'm sitting in this talk, and I'm thinking, ha ha ha, I know what he's looking for. Here is the solution. So afterwards, I went up in a very smug fashion. I said to Ted, Ted, I think that this particular allocation scheme is the way to go. Here, lambda is the arrival rate of people coming in. Mu is how long it takes them, well, 1 over how long it takes them to vote. And then C is some constant that you choose to make everything balance out and everyone to get the right number of machines so that you use up all your machines. So I said, this is the way you want to do it. And to his credit, he actually tried it out. He said, okay, thanks Shane, that's great, I'm going to give that a try. So he tried this out on a simulation model, and he called me, and when the phone rang, and it was Ted, I was waiting for the accolades and everything, and thank you. And he said, thanks very much for a great idea, but it was horrible. And he was much more gracious, but this is true. What I had suggested to him did not work at all. And so I was trying to think, well, hang on. I mean, I do know a little bit of queuing, and I'm pretty sure that's the right answer. And what did I miss? Well, that was my recommendation, and it turns out that number there, the arrival rate, is hugely uncertain in elections. What is the turnout percentage? And that can vary over a huge range, 40% to 60% of the folks who might vote. You get that level of variability in the elections. And so you can do a little bit of prediction beforehand. There are cool regression models and all kinds of things that can give you a better sense of what the turnout's going to be based on what you've seen so far, but it's still massively variable. And in this picture up here, I'm sort of assuming that I know exactly what that value is. And in fact, you don't. So Ted's model accounts for that. He sampled a random turnout and then went with that. And in my mind, I was not doing that. And so I guess one question is this input uncertainty? In my case, I think probably not. I think I probably just misspecified the model. I had the wrong model in my head. But nevertheless, the fact remains we don't know what lambda is. So we should think about that. That's a big deal. So here's the way I think I would tackle this now. And this is pretty much what Ted was doing. So I would say let's let xi be the number of machines allocated to precinct I. And that's a big vector. And the total number of machines that I have to offer to the system is fixed. I've got some primitive numbers here. These are the numbers that are going to get fed into the simulation, and I'm going to think of them as being sort of fixed. You can generate them from your random number generator, but I'm just going to think of them as fixed. Okay, so those are the primitives, the things that won't change depending on this turnout percentage. So they're just the sort of numbers that get fed in, random. And so this is what some people call stochastic uncertainty. And then there's structural uncertainty, which is this guy down here, this unknown scale factor for the turnout. And then what I'm going to do is I'm going to plug all of this stuff into my simulation model, and it's going to spit out a waiting time. And that's this function down here. So this f is really the simulation logic that computes the maximum weight in any precinct. And then what I'm going to do is I'm going to appeal to statistical decision theory, which says, as far as, well, I know about this much statistical decision theory. There's probably people like Steve and other folks here that know a lot more. But my understanding of it says, you look at the random outcome, you plug that into your utility function, and you take the expected value. And then you pick the decision that makes that as big as possible. And that's what I'm doing here. I plug it into a utility function, which I've written as a small u, because it's deterministic. And here I'm trying to reserve capitals for random things. And then you compute the expected value of that. This is your objective function that you want to make as big as possible, maximize utility. And you've got some constraints because you've only got a fixed number of machines and all that kind of stuff, but I want to de-emphasize that. And this is the formulation that I think Ted had in his mind, and I think it's the right way to think about this problem, right? Because these two forms of uncertainty here, the structural and the stuff that comes out of the simulation model itself, they kind of get mixed together, and they're kind of the same thing in this setup. So this is what I would call one-shot simulation optimization. You get one shot at whatever we're doing here, and then the game's over. We're not going to repeat the scenario. So it's the same setup that I just talked about. You've got your decisions, the random stuff that gets fed into the simulation, which doesn't depend on these other parameters. You've got parameters you don't know, that's these guys, and then your simulation logic, and then you compute the expected utility and maximize that. So that's what I would call one-shot simulation optimization. It's, I think, a reasonably clean, coherent story, and that's what you would do to make this decision. This top part is actually just the Bayesian model average. Right, so this is something that Steve was suggesting we should use back in 2001, and I didn't get it back then, but I think I get it now. So thanks, Steve. 10 years later, clunk, I think I get it. So yeah, it's just the Bayesian model average, so it's got a nice background. Computation-wise, this is actually pretty good relative to what we tend to do in simulation. So if you think about this stuff up here, it's your simulation output. We're going to compute the utility function at that point and then just evaluate the expected value. That's easy to do. I just do independent replications. In my voting thing, I just do a whole bunch of potential votes, each time sampling a lambda, then a bunch of w's, and plug it into the simulation. So the central limit theorem tells us that if I run this for c units of computation, then the error is going to be something like 1 over square root of c at any particular point, because I'm just estimating an expected value. So that's nice. We've got fairly, for Monte Carlo, the sort of standard rate here. This notation here just means it's sort of random, but it's of that order. And then I want to, that's how I can do the computation at any individual x, and then I just have to sort of vary x and find the best point. And of course, there's a lot more to this story, but I'm going to ignore that. Okay, so everything seems quite nice. We've got a nice convergence rate. And the key point in here that I want to emphasize is that we treated these two types of uncertainty in exactly the same manner. There's really no difference between them from the perspective of what we're doing here. And we do have the usual problem, where do you get the utility function from? And you know, for the voting machines problem, it's probably what's the chance you get on the news, right? So given the maximum weight, how likely is it you're going to show up on the evening news? Because it's not going to be good if you're up there. Now, one thing that I've done here is I've completely ignored something that I would call the prediction interval question, which is something that the simulation community did think about quite a bit about a few years ago, which is we pretend that there is actually a true lambda somewhere out there that we don't know. There's a real one, and then we want to find an interval that covers this value here where I've plugged in that true value. And I've just completely ignored that because I think it sort of gets washed out when we're trying to make this decision. Okay, so here's a similar example, and it's nowhere near as applied as the previous one, and that's because I had a bit of trouble digging this one up, and that's going to be a theme that runs through here. So here, a completely contrived example. I'm opening a store, and I want to know how many servers I'm going to need at the front desk, and I've got a pretty good sense of how long it takes to serve a customer, but I'm unsure of the customer arrival rate. So I don't know what that will be once I open the store. And what I'm sort of pretending here is that I have to choose X now, so that downstream I just incur whatever customer weights I'm going to have to deal with. And I want to choose that so that the long run fraction of customers with long weights is small. And long run fraction is steady state or something like that. And the reason I'm bringing this one up is that I think this is how a lot of the people in the simulation community tend to think about these problems. We tend to focus a lot on steady state means and things like this, probably as a hangover from the days of Markov chain analysis where you can compute things, you know, and in sort of queuing theory, it's great. I mean, you can compute all this stuff, so it's sort of tempting, but maybe it's a little deceiving. So again, we have that same sort of structure as before, but it looks a wee bit different this time. So here's my decision vector and my primitive numbers that I'm plugging in and my uncertain parameters, which are sort of different beasts. And here's my simulation output. But remember, what I'm going to do now is I'm sort of thinking about it in a different way. I generate a lambda, and then I sort of hold that fixed for ages, and I run my simulation to death. And I compute the true expected value, or the steady state mean of this system. I compute the long run fraction of customers that wait for a certain amount of time. And that's this quantity here. So this is a conditional expectation given an instance of lambda. And then what I'm going to do, and this is kind of where I think we kind of go off the rails a bit, but this is what I think many people in simulation do, is they plug that long run fraction into a utility function. So the utility is associated with this long run fraction, this deterministic quantity, once I fix lambda here. And then I compute the expected value of this because this guy in here is a random variable. And then I maximize that. And that's how I think a lot of people in simulation think about this problem. And probably you guys are a bit more sophisticated, but this is kind of what I had stuck in my head coming over here. And I think it's a bit of a disease. Yeah. So anyway, this is what we've got. And if you think about this now, it's actually quite tricky to do the computation as well, because you first of all have to compute this expected value here, which I'm going to call this quantity here. So we can estimate that. That's no problem. And then we're going to need a second layer of simulation on top of that to compute the outer expectation. There's two layers. And it's in between is this utility function, which is nonlinear in general. So that's not good. So that's going to take quite a bit of work. And then we have to maximize over x. And in fact, in just a wee bit more detail, if we have a utility function that is just the identity, so we're sort of risk neutral, then everything is nice. We're just computing some expected value, and we can do the calculation in the same amount of time that we were requiring before. We get the same error and so forth. But if u is nonlinear, which is really the case that I think we care about, so in this case, well, let's pretend it's smooth, then the computation is a lot harder. And if the dimension of lambda is sufficiently large, where sufficiently large means sort of 3 or 4, something like that, then we're a toast. The convergence rate is much, much slower because you have to have these sort of two layers of simulation, one inside and one outside, and then you have to sort of try to get the computation to work. So at each point that I visit to sort of see how good is this x, it's much slower converging, and so you get a poorer sense of what the objective function is. So anyway, this is what I would call multi-shot simulation. And so where are we at this point? So the one-shot stuff, I think, is a pretty coherent story. We appeal to decision theory, and life is good. Computation is reasonably straightforward. It's of the same order as ordinary Monte Carlo. The multi-shot stuff, you need all this sort of fancy stuff, and I do question if it's real. I think about the problems that I've encountered over time, and I really couldn't find something that I could shoehorn into this framework. But maybe some people here can. In which case, you know, I'll eat my words, and this is a different setup. But I haven't found something like that. But if I think about now the standard toolkit within the simulation community, we don't do any of this stuff. Most of us anyway. We do the usual maximum likelihood estimator, plug that one in, run the simulation, get a decision, done. So why isn't this stuff part of the standard toolkit? And that got me thinking, well, what do other people do, other communities do, who do have to think about uncertainty and make decisions? And that took me, because of my background in operations research, to the math programming community, but it might take you in a different direction. But I was curious to think, well, what do those folks do in the optimization community? And so here we go. Here's sort of three possible things that you might consider from their community, where they do take into account uncertainty. So the stochastic linear programs, you could do chance constraints, which is sort of related to convex risk measures, or you could do robust optimization. And I'm not going to go into this stuff in detail. I just want to bring out one key theme from all of these approaches. So two-stage stochastic linear programming, don't worry too much about the junk up here. The key point is you maximize some function, and it just turns out that this function that you're maximizing as a function of x is concave. Excuse me, concave. So that's good, right? Maximize. You always have to try to remember it, right? It's a bowl. Maximize. That's good. There's a unique, globally optimal solution. There's no locals, so life is good, right? So that's great. That's one of the real features here that makes stochastic linear programming popular, is that it's got this nice structure, which means, first of all, you can solve these problems efficiently because it's concave maximization, and you can also come up with optimality gap estimates, so you know when to stop your algorithms. So lots of really appealing properties, but it's very much like what we were talking before. We're going to compute an expectation up here, but that expectation has particular structural properties, which we didn't have before. So really, structure is the key difference here. I mean, there is a different philosophy going on here. This is two-stage stochastic programming. You know, we can talk about all that, but I don't want to bother. The main thing is the function has this nice structure. Well, what about chance constraints? And here I've taken a bit of a liberty here. Normally, what you do with chance constraints is you maximize your linear function, and then you have a constraint which says the probability that bad stuff happens is small, right? Well, I've put the probability into the objective just to make it look a bit like what we've been talking about before. So I just turned it around, and then I've got a threshold on, I've got a threshold on my objective here. So I just turned it around. It's the same sort of idea. And this is kind of like the one-shot deal, but with an indicator for my utility function. And chance constraints problems are usually quite hard to deal with. So you can turn them into very nice problems sometimes. So usually if you think about each constraint individually, you're probably okay. But essentially these things are actually quite hard to deal with. So the chance constraint kind of world seems to have taken a back seat to the stochastic linear programmers and some other folks in this community. So you don't usually have the sort of convex or this nice structural properties, and so I don't think it's as popular as some of the other systems. And I'm just going to skip over the convex risk measure stuff. And then finally we come to robust optimization. And robust optimization has many different flavors, but here's one kind of flavor. I want to maximize over x, and I don't know exactly what the objective function should be, so I'm going to plop it into an uncertainty set. And I'm going to maximize the worst case objective from within that uncertainty set. Okay, so I look for the very worst case within that uncertainty set of this objective. And to match this to our notation, let's just relabel things, and then it looks like this. So now my W, which was my random stuff, goes here, and we look for the worst possible random stuff within this set. So really what's going on here is we're pretending that nature is playing against us, and we're assuming that every move that we make, nature's going to pick the very worst thing they can. Right? So this is terrorism. This is not nature, right? So this philosophy is kind of a weird one. So why do they do it? Well, it's because under certain conditions, this problem up here has actually got beautiful structure and it's convex again. So there's that theme once again that the math programming community is not starting from some clean decision theoretic kind of basis and then working towards solving the problems. They're starting from clean computation and working their way back the other way. And so that's quite a different philosophy from what we've adopted, and it's really historically based, I think, because they started off with everything being nice and convex. So really, to just finish up, sort of pull all these different threads together, is just a bunch of ideas, really. One-shot, multi-shot, I don't know of any real problems that are multi-shot, but I think that's how a lot of folks in simulation think about it. And from that perspective then, given that we're going to just sort of think about all these sources of uncertainty as being the same thing, is there really such a thing as input uncertainty, or is it just kind of the same deal? You know, it's a bunch of random numbers that you plug into your simulation. The popular optimization paradigms that we sort of quickly went through, the key theme is convexity. They're really looking for structure, and they're not too worried about whether it looks like decision theory at all. So that is something that's sort of, I think, food for thought for our community, which is that a lot of those methods up there are actually quite popular and used a lot. And so we don't have those first two properties, that nice computational tractability that you get with convexity. And so maybe we should think a little bit about subclasses of problems for us that do have those properties, and that might be a fun thing to take a look at. So I'll stop there. Thanks very much.
Any quick questions? He's running a bit ahead, so if he's got some questions. Yes, Barry.
So your W and your capital lambda, which you're treating it as the same in one shot, seem to me to be very different, because how do you pretended that the uncertainty in the capital lambda was fully specified, whereas I completely understand how W is specified. It's the uniform or whatever is driving.
Sure.
And so it seems like there's another level of uncertainty. Even when you
I was definitely hiding an awful lot there, right? So there's the whole world of, let's suppose that lambda is random, and let's pretend it's uniform on some range. Which range? And we're all going to argue about that. And so, yeah, you'll probably get a bunch of folks that disagree about that, but in the end, you've got to do something, right? And so I think it's true that there is probably more debate about what that distribution should be, but as a tool for making decisions, I'm just going to wash them all together, and I'm not going to worry about it.
But then instead of conditioning on a constant, you're conditioning on a distribution. Your results are then still conditioned.
True. Yep. Doesn't faze me in the slightest, actually. No, I think it's a perfectly valid point, which is this sort of notion of which numbers are things that you can argue about, which can you not, and completely agree with that notion. We're stuck there. Such is life. Got to make a decision in the end.
The other issue about lambda is there's a philosophical issue about stationarity. Do we really think we have a distribution or not? And if we think we have a distribution, then you can't change the distribution parameters randomly like you change the uniforms, or you won't capture that.
So I think a closely related point here is something that Steve brought up when we were having a beer yesterday talking about some of this stuff, which is that in that one-shot deal with the shot, you're not going to fix your staffing for all time, right? You're going to adapt and you're going to try to learn what that distribution is. So if you actually build all that adaptation and so forth into your simulation model, you're back in the one-shot setting, but just with a longer horizon for the simulation. So I sort of think of those as one thing. Yeah.
Anyone who's willing to think lambda is a constant is just fine. But, that would be it. And our next.
Okay.
Thanks, Shane.